$1. That's what it costs. $1 to stabilize 10 gallons of gasoline. Not for a year, not for two, for years, possibly a decade. The compound is called butylated hydroxytoluene, BHT. Its CAS registry number is 128-37-0. The FDA classified it as generally recognized as safe in 1959. It's in your cereal, it's in your cosmetics, it's in military jet fuel, and it costs about $1 per 10 gallons of gasoline treated. Now here's what you've been doing instead. Every year you dump your stored fuel. You drive to the station. You pay $30 to $50 to replace 10 gallons. Over a decade, that's $300 to $500. Gone. For the same 10 gallons. The fuel additive industry generates $1.4 billion annually. They sell you 12-month solutions to a problem that was solved in the 1940s. Not because the chemistry doesn't exist, because the EPA's additive registration framework under 40 CFR, Part 79, was never designed for storage performance. It was designed for emissions. Every commercial stabilizer on American shelves is formulated to that ceiling, not to what's chemically possible, to what's regulatorily convenient. By the end of this video, you'll know the exact compound, the exact dosing range, the complementary additive the military uses alongside it, and the 5-step protocol that petroleum chemists have understood for over 70 years. The question isn't whether this works. The question is why nobody's selling it to you. Welcome to the channel. What we do here is simple. Industrial chemistry, to military logistics, and published science generate knowledge every year that never reaches consumer shelves. Not because it's classified, because there's no profit in translating it. This channel is the translation. Subscribe if you want to keep reading the chemistry instead of the marketing. We're building something here. A community that verifies before it buys. Now, let's talk about why your gasoline goes bad in the first place. Gasoline is a mixture of hydrocarbons, and hydrocarbons are under constant chemical attack from the moment they leave the refinery. The process is called autoxidation. It's a chain reaction. And once it starts, it feeds itself. Here's how it works. Initiation. Heat, ultraviolet light, or dissolved metal ions strip a hydrogen atom from a hydrocarbon molecule. That creates a carbon-centered radical, or an unstable molecule desperate to react. That radical grabs oxygen from the dissolved air in your fuel. Now you have a peroxy radical. This is the propagation step. The peroxy radical steals a hydrogen atom from another hydrocarbon molecule. That creates a hydroperoxide and a brand new carbon radical, which grabs more oxygen, which creates another peroxy radical, which steals another hydrogen. One initiation event can generate thousands of radical cycles. The chain sustains itself, the hydroperoxides accumulate, they decompose into alcohols, aldehydes, organic acids. These polymerize into gums and varnishes. The dark residue that clogs injectors, coats carburetors, and ruins engines. That's not contamination from outside. That's your fuel eating itself from within. Now, enter BHT, a molecular weight 220.35 grams per mole. It's a hindered phenol, a specific class of antioxidant. Here's what it does. BHT donates a hydrogen atom to a peroxide radical. That terminates the chain. The radical is neutralized. But here's the elegant part. The phenoxy radical that BHT becomes is itself stabilized. Two bulky tert-butyl groups flank the oxygen, physically shielding it from further reaction. The radical can't propagate. It just sits there, inert. Each molecule of BHT neutralizes two peroxy radicals, 2 chain terminations per molecule. The critical variable is concentration. At the low doses found in commercial stabilizers, the BHT is consumed within 12 to 24 months. The radicals eventually overwhelm the available antioxidant molecules. That's why Stabil tells you to rotate annually. But at elevated concentrations, surplus BHT molecules remain in solution long after the initial radical assault. They keep intercepting, month after month, year after year. Concentration is the secret. It always has been. Everything you thought you knew about the shelf life of stabilized fuel was actually a statement about dosing, not about chemistry. This is the kind of research that goes deeper in our vault. The vault is where we archive the full technical breakdowns. Commercial stabilizers like Stabil and PRIG are the baseline. They work within the limits they're designed for. But the vault goes beyond those limits. Strategic water purification, long-duration food preservation chemistry, off-grid medical supply protocols, energy storage beyond what consumer products offer. No fluff, no filler, just the documentation. Link is in the description. But first, let's talk about why no company in America sells what we're about to describe. The EPA administers 40 CFR, Part 79 and Part 1090. These regulations govern the registration of fuel additives. Any manufacturer selling an additive for use in motor fuel must register the product with a specific composition within defined ranges. Any deviation from that registered composition is a federal violation. These rules exist for a legitimate reason: air quality, emissions control, public health. The EPA is not a villain here, but the system has a side effect. It creates a ceiling. Every consumer fuel stabilizer on the shelf contains BHT-class antioxidants at concentrations calibrated to regulatory compliance, not to maximum storage performance. Now, here's where it gets interesting. There's a second additive, one you've almost certainly never heard of: N'-disilylidene 1,2-diaminopropane. It's a shift-based chelator, a metal deactivator. Remember the initiation step in the autoxidation chain? Dissolved metal ions, copper, iron, manganese, accelerate that step dramatically. They catalyze the formation of radicals. Even trace amounts of dissolved copper can multiply the initiation rate. This chelator wraps those metal ions. It bonds to them, encases them in a molecular cage. The metals can no longer catalyze radical formation. With the catalysts neutralized, the radical load on BHT drops significantly. The antioxidant lasts longer because it faces fewer attacks. The two additive system: antioxidant plus metal deactivator. That's not experimental. That's NATO specification F34. That's JP8 military jet fuel. Aviation and military fuel logistics have used both additives at concentrations that exceed anything in consumer products for decades. In a spec markets, the metal deactivator under trade designations like AO29 for aviation applications. The chemistry is published, the specifications are public, the military uses it. You just can't buy a consumer product formulated this way. The American fuel additive market has a structural problem. BHT has been off patent since the 1960s. You cannot patent it. You cannot create a proprietary formula around it that competitors can't replicate. No patent means no margin. No margin means no marketing budget. No marketing means no consumer awareness. And there's a deeper incentive problem. If you sell a product that stabilizes fuel for 1 year, you have a customer for life. Annual purchases, recurring revenue, predictable quarterly earnings. If you sell a product that stabilizes fuel for 5 to 10 years, you've sold 1 unit. The customer disappears. Wall Street does not reward that business model. The EPA registration process requires health effects testing for any new additive formulation. That testing is expensive. No company is going to spend millions registering a product built on an unpatentable compound that eliminates repeat purchases, so the product doesn't exist, not because the chemistry fails, because the economics don't support it. Now consider Japan. Japan imports 97 to 99% of its petroleum. After the 1973 oil crisis, Japan built one of the most aggressive strategic reserve programs in the world. The Japan Self-Defense Forces maintain approximately 240,000 active personnel. For a nation entirely dependent on imported fuel, every gallon stored is a strategic asset. There are claims that JSDF protocols achieve 10-year fuel storage viability using elevated concentration antioxidant systems. I want to be direct with you. This specific claim is unverified in publicly available English language sources. I have not seen the original Japanese documentation, but it is chemically consistent with what elevated BHT concentrations achieve under laboratory conditions. A country that imports virtually all its oil has every incentive to push fuel longevity to the absolute limit. No one profits from telling you this. If this is the kind of knowledge you want to keep receiving, you know what to do. This information exists in petroleum chemistry textbooks and military logistics documents. Our job is finding it, verifying what we can, and translating it into something you can use. Subscribe. Share this with someone who stores fuel. The link to the vault is below. Now, honesty. Here's what we don't know for certain. The 10-year figure is a theoretical upper bound. It's extrapolated from BHT's radical scavenging kinetics at elevated concentrations. 5-year storage is more widely supported by anecdotal evidence from long-term preparedness communities. No independent peer-reviewed study has tested this exact protocol with modern post-2006 reformulated gasoline over a full decade under controlled conditions. BHT itself degrades under ultraviolet light. The relationship between UV intensity and degradation activation energy follows the equation. Activation energy equals negative 1.878 times the natural log of intensity plus 74.56. What that means practically is even brief exposure to sunlight compromises the antioxidant. Total darkness is not optional, it's essential. Ethanol-blended gasoline cannot be stabilized by this method. Ethanol absorbs moisture from the atmosphere. That moisture causes phase separation. The ethanol and water sink to the bottom. The gasoline floats on top. No antioxidant solves a mechanical water absorption problem. You need ethanol-free fuel. period. Modern gasoline is less stable than older formulations. The lower sulfur content and altered aromatic profiles mean today's fuel oxidizes faster than what was available 20 years ago. That's not a reason to skip stabilization, it's a reason to take it more seriously. On safety. The International Agency for Research on Cancer classifies BHT as Group 3, not classifiable as to its carcinogenicity to humans. Animal studies show conflicting results at extreme doses far beyond what this protocol involves. BHT has been in the human food supply since 1954, and gasoline itself is dangerous. Fire risk, explosion risk, vapor toxicity. Your local fire code governs how much you can store and where. Follow it. This channel is not your fire marshal. That transparency matters. Now here's the protocol. Step 1. Source ethanol-free gasoline. The website pure-gas.org maintains a searchable database of stations selling ethanol-free fuel across the United States. Use it. Ethanol-blended fuel is incompatible with long-term storage, regardless of additive treatment. Step 2. Obtain food grade BHT powder. CAS number 1, 28-37-0. Purity 99% or higher. This is available from bulk chemical suppliers. A 1-pound bag costs roughly $15 to $20 and treats hundreds of gallons. Step 3. Dissolve BHT in a small volume of gasoline before adding it to your storage container. Target dosing range is 100 to 500 parts per million by weight. For 10 gallons of gasoline, which weighs approximately 62 pounds, 100 parts per million equals roughly 2.8 grams. 500 parts per million equals roughly 14 grams. A basic digital scale accurate to 1/10 of a gram handles this easily. Dissolve the powder in a mason jar with a cup of gasoline first. Stir until fully dissolved, then add to the full container. Step 4. Add a metal deactivator. Aviation-grade metal deactivator products are available from aircraft maintenance supply vendors. Follow the manufacturer's dosing specifications. This chelates dissolved metal ions and dramatically reduces the oxidative load on your BHT. Step 5. Fill approved storage containers. Steel jerry cans or HDPE fuel-rated containers. Fill with minimal headspace to reduce dissolved oxygen. Seal completely. Store below 70 degrees Fahrenheit in total darkness. A basement shelf away from any ignition source is the standard approach. Inspect seals annually. Total additive cost, approximately $1 per 10 gallons treated. Let that settle for a moment. The same antioxidant that's been preserving your breakfast cereal since 1954 preserves gasoline. The same metal deactivator in NATO jet fuel specifications is available from aviation supply catalogs. The chemistry has been published for over 70 years. Militaries deploy it. The cost is negligible. The United States Strategic Petroleum Reserve stores crude oil, not refined gasoline. In a refinery disruption scenario, whether from natural disaster, infrastructure failure, or supply chain collapse, there is no government gasoline reserve waiting for you. Crude oil in a salt cavern in Louisiana does not power the generator in your garage. The only barrier between you and multi-year fuel security is an information gap. Maintained by a regulatory framework designed for tailpipe emissions, not household preparedness. Sustained by an industry that profits from selling you the same 12-month solution every single year. Built on a compound so old, so cheap, and so unpatentable that no corporation will ever spend a marketing dollar telling you about it. A bag of white crystalline powder, a steel container, a dark shelf below 70 degrees. That's the difference between mobility and immobility when the supply chain fails. The chemistry was never the secret. The secret was that no one had a reason to tell you. Now you know.